Hi, this is Russ Anderson. Accurately calibrating lenses takes a laboratory setup with a nice big super accurate coordinate measuring machine, which none of us have. So the question here is, how well can we do without one, i.e. without the ability to measure points out in 3D? And a tape measure just isn't going to cut it. So here I'm going to show what I call a zero knowledge technique, where we're doing calibration without really knowing that much about what we're using to calibrate. So it's kind of a crazy, awesome technique, very mad scientist. So the idea is to use a holiday laser projector to put lots of dots on the walls of a room. And then we're going to spin the camera around 360 plus degrees on the tripod and use the resulting set of data for the calibration. I'll point out the whole thing happens in the dark. So here's the sort of thing that you get, and I'm going to show you how the calibration goes using it. So I've opened up the shot, and I'm actually going to go and on the res tab I'm going to switch to just the green channel, and that's just to save the total amount of memory that we have, because this is a pretty long shot. So you can read in the manual more about how to do this setup, but the idea is that you do need to do a nice slow and deliberate scan so that Synthi is able to track exactly what's happening. So I'll point out, when you open up a shot like this, it can take a while for Synthi to first index the shot, which you'll just get a little spinning cursor during that period of time. And then, you're seeing the time now while it goes through and opens the, reads each of the frames and does the conversion to a black and white image, basically. So we'll just wait a second while it does that. If the lens that we're using is an anamorphic lens, when we initially open the shot, you want to keep the anamorphic correction off. So you don't enter that anamorphic ratio so that it stays with the square pixels. And that improves the image processing. And that's especially necessary when the anamorphic ratio is a full 2. If it's just 1.3, maybe you don't need to worry about that. You can get the image straightened out to its full width in the first place. Okay, so now we're going to go over to the features panel, and we're going to switch to RandomDot Processing mode that's optimized for handling this kind of pattern. You notice it's quite a bit different than a normal sort of image where you can look at the overall context of the image. Here we're looking just at tiny little dots and the patterns of the dots to be able to track them. So it's a little more difficult, and there's a slightly different algorithm that's used to do that. So we select that up here. Now we're also going to go take a look out here. We can turn on the AutoBlip Mode. What we're going to do is just scrub through the shot to some point where the pan is in progress, and you notice that we will get some motion blur, and that is one of the reasons when you're doing the setup you actually want to keep the shutter time still fairly short. We're going to go and adjust this feature size a little bit. So depending on the size of these dots in the image, you want to make sure that you A, get them, B, that you don't have duplications. When the dots get to be longer, a little bit more stretched out, you can actually wind up, getting two little dots within the same spot in the image. So you might need to adjust this size here a little bit to account for that. And that's especially true if you've got a narrower field of view. Here our dots are really fairly small, so it's not an issue. But, as you can see, you can kind of get the same sort of results over a fairly wide range of sizes. So that's a good thing. And at the smaller value, you do start to pick up a bunch more of the spots, and some of the really small spots are probably spurious, but you get to control that a little bit. Now we're also going to take a look at the tracker parameters here. Now, important one is what the minimum track length is, which depends on how fast the thing is spinning and what the field of view of the camera is. If the field of view of the camera is fairly small, then even if you're moving the camera slowly, it can still take only a relatively small number of frames to have a tracker come on to the image on one side and then exit the other side. So we want to make sure that this minimum tracker length isn't so small that the trackers never are able to reach it. So here I think the 80 is the default value. So we could just start here. So say it's around 200. And if you just kind of keep your eye on the same general area, it's winding out somewhere over 400 frames before roughly they're going off. So the minimum tracker length of 80 is going to be good. And we're going to be wanting to make sure that we've got plenty of trackers per frame. And we get to set a maximum tracker count. Now notice these numbers are different than you get by default, and they're being set as a function of this RandomDot mode. So they're higher, and depending on exactly what you have in the image, you can make these numbers even larger if the situation warrants. But here we'll just go with the default values. So we're going to do a clear all blips just to get rid of the ones that we created. And then we're going to do blips on all frames. So now it's running through and doing that same blip finding process throughout the entire 800-ish frames of the shot. Now that that's complete, we can do a peel all, which is going to take all the blip data that we have and create trackers from it. So we got about 4,000 trackers there, exactly 4,000 our limit. So it's quite a few. One thing I'll point out that you don't want to do at this point, you don't want to do anything that would clear the blips. The blips are going to be used later in the process also directly. So don't delete them. Don't do a tracker cleanup that deletes them either. At this point, if you have an anamorphic shot, now you can go and put that anamorphic factor back in and get the full kind of actual final aspect ratio of the shot. Now we are going to go and do some tracker cleanup at this point. So we're going to go over to the graph view and we'll start making some adjustments here. You don't need the figure of merit. We'll separate these guys out a little bit. So we have all 4,000 trackers being selected at this time. One thing you can notice from this right off the bat is that there's some tracker that's sitting here down at a zero velocity. So that's telling us that there's a tracker that doesn't move. And typically that indicates a dust spot or a bad pixel on the sensor. So we're just going to hit delete on that. Same with that. Well, that was bad. Took out all the trackers. So let's go back to what we were doing. We want that one. Delete that one. Looks like there's another one there also. So now we're going to start doing a little glitch fixing. And there are a couple of different kinds of glitches that you can see. One are the kind that are just at the beginning and end of a path. Typically right as something goes off at the edge, it may just kind of hang right at the edge, a little bit partially on and off. The other kind of glitch are where something jumps to an incorrect spot temporarily and then jumps back. And both of those types are fixed automatically by the glitch fixing tool. If we go through and start clicking on them, you'll see in some cases there may be a slightly longer glitch. So we can just work these little tails out. They're not going to be helping us at all. We don't have to get every last little thing. It's kind of a quick pass here. So this is one that we can get. I'm just going to hold down Control and we'll look at that. See, that's the kind that it's just jumped to an adjacent spot. Again, we'll take a look at that. Now that's kind of more complicated sort of thing. So let's just go, and I'm going to hold down Shift and split. So now we have just this one. We'll get rid of that. And again, I'm using the Control A from time to time to select all of these things. Again, we'll go and take a look at there. There's really not any point to splitting that. We can't really do the tracker cleanup at this point because we haven't solved this scene at all, and we're not going to. So we're just using a little human judgment on what to take out. So we'll just split this and delete that guy. So I'm just using the same basic combination of clicking on things that are problematic, sometimes splitting them, just taking advantage of this glitch fixing tool. And at some point we'll just declare victory that we've gotten really the majority of the larger problems out of this. So that was our glitch fixing stage for this. And now we're ready to start with the calibration. So let's just run back to the tracker view. I think we'll turn off the trails. So we're going to use the lens master calibration, and we'll just run through the different settings here. We want to be sure to use the random dots method, and we're going to be panning the full 360 degrees. And this is going to tell it to look for the spot where it wraps around exactly to 360 degrees, because that's a really important piece of information. So we've got a couple of different kinds of fisheye lens that we might have. So we'll just go with the first one of those to start with. And here, because we have this much larger set of calibration data and the fact that it wraps around the 360 degrees, we can go with a full quartic distortion calculation. We're going to definitely be calculating the lens center, definitely be calculating the lens field of view. Just throw in a estimated field of view, and our lens radius is 1. There's not any vignetting here. And one important thing, we're going to turn on the rolling shutter correction and supply the value that's appropriate for this. This is a Panasonic GH4 running at 4K mode and 24 frames per second. So this is the rolling shutter value that we've determined previously for this combination of camera settings. Now you notice that the camera is moving pretty slowly, so it doesn't seem like the rolling shutter should be contributing that much of an effect. But if you think about it, well, we're looking for effects that are small in the first place. We're looking for an accurate lens distortion calculation. So even though it's a small value, a small amount of distortion, or rolling shutter effect that's involved, even if that contributes a pixel or 2 pixels at the slow speed, that's still significant to what we're doing here. So it's important to get that rolling shutter value in here. So with that set up, we'll hit OK here. And since this is a wide field of view, we're just going to go with the 360 VR output method. That solves us from having to worry about too much else also. And we're going to apply it to the scene. So now we're going to go and let this run. So this will take a little while. It puts all your processors to work, so we'll just wait for it to do its thing. Note that while this is running, SynthEyes appears to be completely hung because this process does not run in the background because it's driven by scripting at this point. So you just have to be patient, give it a chance to go do its thing. And now we have our results. You'll see, first off, that this is the 360 VR setup. So we now have a very much wider field of view, and it's actually chosen some output image format that's fairly large based on that and based on our input size. And we have everything all spread out throughout this 360 VR image. We're looking in all possible directions at the same time. So you'll see that our error is quite low. You'll see that there's a couple different field of views. The one that's really of interest is this true field of view, which is the field of view of the left and right edges of the original image. You'll see some coefficients here. They are kind of offsetting coefficients, but here we're trying to do as well as we possibly can, and in fact did come out that way, with a pretty nice solution. Okay, so now some more subtle things. You'll notice that we're now sitting at frame 647, and that is telling us where it found the loopback point, where it came as close as possible to traveling exactly 360 degrees around. And that's also, if you look, you'll see that there are some little key markers here. Hopefully the compression won't mangle those up too badly. But there are key markers. There's a key right at this very last frame. The last key is the wraparound part. So if we start at this point and we just go, all the way back to the beginning, basically the image shouldn't change in that process. So let's go, we'll go back to our 647. I've zoomed in enough so that you can actually see the modified image. And now I'll go back to the beginning again. And you see that the actual trackers, some of the dots have trackers and others do not. And so that jumps around a little bit. But the dots themselves are staying pretty much in the same place because we've identified the correct loopback frame where it's done the 360 degrees. Now, in the event that that process didn't work out right, if the tripod was bouncing around too much for it to refine the right spot, you can actually help synthesize out a little bit to be able to find that. There's a description of that in the manual. You'll also see that there are groups of keys throughout the shot where there's a row, several keys in a row. And then there are areas where there are not any keys in the camera path. And that information is telling you which frame Synthesize actually used to do part of this process. So if you go and look at one of the keyed frames, you can go and zoom in and you'll see that things will line up. Now, admittedly, my responsiveness is not too high here because Synthesize is currently spending a whole lot of effort to do all the conversion from the fisheye to the 360 VR format. So maybe, let's see, let's turn that off. So here we've got a frame, and what you see are, just like with a regular 3D solve, you see that the 2D tracker is there and the computed direction, because basically all the trackers are far trackers. They're all in the middle of the 2D trackers. If you pay attention really closely, you'll notice down at the bottom they're shifted in the one direction, and up at the top they're shifted in the other direction. So what's going on? Well, that's due to the rolling shutter. That's telling you literally how much rolling shutter there is, and it's a non-trivial amount. You can see if you look down at the bottom as the coordinates change, there's definitely a couple of pixels due to the rolling shutter effect. So the camera view display doesn't correct everything possible for the effect of the rolling shutter. If we'd not done the rolling shutter calculation during the calibration, everything would line up perfectly, but the errors would be higher because we wouldn't be correcting for the rolling shutter effect. So I just wanted to let you know a little what you're seeing there. I'll also point out, if you go and look at the last frame, you'll actually see that there are, in some of these spots, or perhaps it's the first frame. Anyway, there are links between some of the trackers and the different positions. Here you go. Here's a link between these two trackers. One of these trackers is from the beginning of the shot, the other is from the end of the shot. So that's giving you an idea of how the linking process wound up, how accurately that whole process wound up between the beginning and end of the shot. And I will, where by end I mean the spot where it reached the 360 degrees as close as possible. And I'll point out that Synthesize is actually computing the perturbation at that closest frame. So it's trying to match the trackers as close as possible to what happened at the beginning. So a bunch of complicated seeming little details going on there, but really at the end of the day what you're more concerned about is what you get here as the actual calibration data. So we could go and do this whole process repeatedly with the different types of lenses, the aqueous solid lens, the orthogonal lens, or ortho, whichever it is, lens, and so on, and compare them. And what you'll find out is that with the quartic distortion being present, that there isn't so much of a change in the final results, because basically the quartic distortion is able to cover a lot of the difference between those different distortion curves. So it's able to compensate for the differences, so the error winds up about the same. Now, some of the other numbers are all changed, but the number that's going to stay the same quite nicely is the true field of view. And you'll still wind up getting basically the same final map that takes it from being a fisheye shot to a 360 VR shot, or whatever your final output format is. So just to summarize, we've taken a scene where we're just looking at a whole bunch of dots and we don't really know where they are, and we're getting really a ton of data from them that really covers the entire field of view of the image and provides a long sequence of data for each of those points. And from that, we're able to get some really nice calibration data. The fact that it wraps around to 360 degrees exactly is also a powerful, powerful technique for making sure that we're getting the right result. So that's really a key thing. You can do this calibration without that, but I don't really recommend it as much. It's a powerful technique, a zero knowledge approach, if you like, of saying, well, if we get back to where we started, then that tells us, well, no matter how far we went around, in the meantime, we still have to wind up at exactly the same spot. So it's kind of a super accurate measurement that's not, you don't have to measure at all. So that's pretty cool. So here we're doing that with the random dots. You could actually probably do this just with a more normal scene also. If you wanted just to get the field of view accurately, you can probably do this in an outdoor scene or a very cluttered indoor scene, as long as things are fairly far away, and get a nice field of view number based on that 360 degree travel. So it's kind of a cool technique. I like it. So I hope you've enjoyed this mad scientist moment, and thanks for watching.